Hello guys, nice to see you.
Good afternoon, Professor.
Hi. So we got already real winter yesterday. I don't know how in other parts of Kazakhstan, but in Astana, that's already quite a lot of snow, getting cold. Okay, so I believe you received my emails regarding the midterm, which is coming, like midterm number 3. So nothing special about this one. Similar procedure, use long kappa, and you will get 7 problems. My recommendation, as I mentioned before, read them first carefully, like all 7 problems, and pick up those which are easier to solve, finish with them, and then you will have time to think about problems which are not so straightforward for you. It will create good conditions to get minimum points which you can get by solving easier problems, and then you still have a chance to solve difficult problems. But if you focus all your attention on the difficult problem at the beginning, you may solve it or may not, but then you don't have time to deal with other problems which could be done much faster. And yeah, be careful, because read and think about these conditions which are specified in the problem, since it indeed matters at the end. Also, I believe that soon, maybe you have already gotten this, but maybe soon it will be sent, this request to participate in a student survey, like answer some questions on the course and how you experienced this studying online and stuff like that. So all students are welcome to participate in this survey. It's important for us to hear some feedback from students, how it goes for them. Okay. Yeah, so another thing, it's mentioned also in the email, but this message which I have sent, the midterm will include topics up to sound, I guess it's chapter 17. So it will be included in the midterm. All chapters which are after sound, like already thermodynamics, they will not be included. So I guess everyone has already joined who wanted, and we can proceed further with our discussion. Okay. So far, we were identifying the state of the system using 3 main parameters, which are temperature, pressure and volume. So these parameters are called state parameters because they define the current state of the system. For instance, what we discussed during the last class, heat, it's not a state parameter because it doesn't define the state. It only shows how the state will change, because we either provide heat and how much, like either some amount of energy crosses the boundary of the system going in or outside, and quantity matters. So heat is a so-called transfer parameter, which defines how, in which direction and how much the state, current state of the system will be changed because of this heat. So there is another important transfer parameter, which is work done by the system or done on the system. So let us consider such a system with cylinder with a piston. So we have certain volume of gas at some pressure P, so some volume of gas at some pressure P. So this is A, the area of this, of the base of the cylinder. And let's have system like Y coordinate, which goes downwards. So there will be some force with which this system stays under equilibrium, and there will be some force from the side of gas on this piston, and this force will be like its value, like amplitude, the magnitude of this force will be a product of pressure and area of the piston or of the base of the cylinder. So if there is some, because of some external influence, we push this piston downwards by some distance dy, then some work will be done on the system from outside. Let us figure out which work this will be. So first of all, we can define our force, which acts from down towards top, as like minus PA unit vector J. So it's in the opposite direction from the axis Y. Then we have some change in the radius vector, position vector, which is dy times, times J. Sorry. So now we know from definition that work done by force is equal to the dot product of two vectors, of the force vector and the displacement vector, or change in the position vector. So that's why we can write F dot product to dr. So since these vectors are parallel, we can skip the vectors and just use its magnitudes. So in this case, it will be minus E times A times dy. So this part is nothing else as dV, change in the volume, Thus, we end up with minus P dV. So this is some elementary like work which is done by changing position of the piston by very small displacement dy. So in order to, if we have some want to calculate the total work done on the system, we need to integrate it. So in general, this work will be an integral, like minus integral V initial V final times P dV. And this minus here tells us that we reduce volume. So, and that's why this system, this work is done on the system. That's why this work is negative. So if we let system to expand, then system does this work, and this work should be positive. So we can also consider this in some system of coordinates for pressure and volume. We'll come back to this a bit later, but let's have just first look at it. So let's have state 1, state 2. There is some transition between these states. Goes from state 1 to state 2. Here we have pressure, here volume. So we have volume at state 1, volume at state 2. The same we can show for pressure. P2. Yeah, and according to this definition of work, this will be area underneath this curve, which defines dependence of pressure on voltage, but with the sign, with negative sign, because this work is done on the system. Okay, so once we finally introduce all state parameters and two transition parameters, which are heat and work, we can proceed further and formulate first law of thermodynamics. So first law of thermodynamics is nothing else as like some more specialized formulation of law of conservation of energy, which is very broad and general. So we can write that change in the internal energy of any system is equal to the sum of heat, Q, plus work, which is done by the system or on the system, depends on conditions. So this is a formulation of the first law of thermodynamics. And now we can consider this first law of thermodynamics at different conditions. First of all, if we have some isolated system. Isolated system means that it has no interactions with external surroundings. And in that case, Q is equal 0, work. So there is no transfer of energy between the system and surrounding. and work is also equal to 0 since it doesn't interact in any form with surrounding. So in this case, internal change of internal energy is also 0, and internal energy is constant. So for isolated system, internal energy remains constant because there is no transfer of energy, neither in nor out of the system. So another option, we have some cyclic process, means that the system comes from state 1, goes to some state 2, and then repeats back to state 1. Since state of the system is described by three state parameters, which is pressure, volume, and temperature, if the system made some changes and then came back to initial set of state parameters, means that another state parameter, which is internal energy, didn't change because it depends on the other three state parameters: volume, pressure, and temperature. That's why it doesn't matter what is going between this during this cycle. If it comes back to initial state, change in internal energy is also 0. So it doesn't remain constant internal energy, it changes while systems go through the cycle. But when it comes back to the initial set of parameters, it will possess the same internal energy as it was at the beginning. So during this, in order to keep this value 0, change of internal energy, heat should be equal to negative work done on the system, or negative heat should be equal to positive work done by the system. Then we end up kind of canceling each other, these two parameters, and change in the internal energy is not observed. Okay, now let us maybe consider, so these cases are very general, which are applicable to a broad range of systems. Let us probably be more specific now and consider some applications of first law of thermodynamics in the case of ideal gas. So let us again consider our lovely system, piston, cylinder with a piston, and we have some ideal gas here. Some work can be done on this ideal gas system, and also some heat, some energy can be transferred. And this system, as a result of these changes, will exhibit some change in internal energy. So these processes can follow different conditions. And first of all, we consider so-called adiabatic process, which is a process when there is no exchange with energy between the system, so the heat U is equal to 0. So this can be realized either by some excellent thermal insulation or by performing this process in a very short time interval, that this energy exchange with environment is negligibly small. Because during this very short period of time, not much energy can be transferred. So in this case, since we exclude heat from this process, we deal with change of internal energy equal to the work. So depends if work is done on the system, when its work is positive, then change in internal energy is also positive. So it means we increase internal energy of the system by performing some work on it. If work is negative, then of course change of internal energy is also negative. And that means that internal energy is used of this system, is used to perform some work, and that results in the reduction of the internal energy. Okay, and obviously with positive increase of internal energy, temperature of the system increases. Obviously with decrease of internal energy, temperature decreases. So one of the example of this adiabatic process is formation of thunder clouds. It's considered as example of adiabatic process in nature. So it doesn't happen very fast. However, due to huge volume of air masses which are involved, like heated, warm air from the pre-surface area, it rapidly goes up because of convection, and this system performs. So this massive volume of air is just so big that you can neglect any heat exchange with environment of the central part of the cloud structure. And because of performing some work against environment, like atmosphere, this temperature of this system drops. And as a result, this humid air, because of reduction of temperature, start to condensate. The humidity in air start to condensate and form drops of water, which then participate as rain. Okay, let's go to the second important case. So this is first one, adiabatic. If we consider now process with constant pressure, which is isobaric process, we had some discussions previously on ideal gas state parameter changes and relationships for adiabatic sorry, not adiabatic, but isobaric, volumetric, and isothermal processes. So here it's from the point of view, not state parameters, but from the point of view of first law of thermodynamics. So in this case, if we have second pressure constant, isobaric process, both heat and work may be not equal to zero. So both processes, like energy transfer through the boundaries of the system and work done on the system or by the system, can happen. And in this case, work is calculated as minus P, which is constant pressure, times V final minus V initial. So since we have P constant, we don't have integral here because we just need to know change in the volume of the system. And since we have this sign negative here, so this specific case is for work done by environment on the system. Okay, another option for consideration will be constant volume, so-called volumetric process or isohortic process. So in this case, change in volume is not observed. If there is no change in volume, there is no work done by the system, because work is product of force, like dot product of force and displacement. If there is no displacement, which in our case is change in volume, means that work is done by the system equal to zero. So in this case, work is equal to zero, and change in internal energy is defined by heat, Q. So means, I don't know, some example like you start to heat some gas inside a tank, like some container. It doesn't expand because these containers walls are keeping gas from expansion, but it gains energy because we have this heat transfer. And as a result, internal energy increases, temperature and pressure also increase, but volume doesn't increase. Of course, until some moment either you stop heating the system or this container will be damaged by the internal pressure, and this tank will be exploded. So there is one more system, one more case to be considered is or we have constant temperature. So it isothermal process. So in this case, let us probably have a plot similar to that one which we did before. So we have voltage, pressure, we have initial and final state, and some transition between them. Okay, so this dependence pressure on voltage will be defined by the equation, ideal gas equation. So just to remind you, we have P times V equal to M divided by mass divided by molecular mass times R, gases constant, universal gaseous constant, times T. So if we have T constant, in the right side, every term is constant. So if we don't lose material, universal gas constant is constant by definition. Temperature is constant. That's why we have here constant from the right side. And this dependence will be some this dependence which is shown on the plot will be defined by this equation. So again, we have some initial volume and final volume, final pressure and initial pressure. So work done by the system in this case. So we see that volume is reducing, going from larger value to smaller. No. In the contrary. So here, like, volume is increasing. So system is doing some positive work. So system is doing work on environment, not environment on the system. And we can write that the work which is done will be integral of the product P times dV, V initial, V final boundaries. So in this case, we can express pressure from this equation, from ideal gas equation, substitute instead of P, and we will get integral initial to final and let's maybe, in order to make it less crowded, let's substitute m divided by molecular mass. Let's call it nu. Then we will have nu RT divided by V times dV. And since everything what we have here in nominator R is constant, it doesn't depend on volume, we can take it out from the integral. So it will be nu RT integral dV over V, from V initial to V final. And here we also need to consider how to integrate this function. So just to remind you, integral of dx over x is equal to natural logarithm of x. So we can write here will be nu RT times natural logarithm of V in the interval from V initial to V final. Yeah, so this is how we determine work done by the system during the isothermal process. Now, need to focus our attention also on energy transfer mechanisms. So we mentioned that heat can be as process of transferring energy through the boundary of system. can happen, but we don't specify exactly how this process is carried on. So there are three mechanisms for transferring energy, and we will discuss them now. So assume that we have some plate and from one side we have T1, from other T2. So these side surfaces of the plate, they possess different temperatures. Then T1 is larger than T2. We have some heat, some energy transfer from first surface to the second surface. And we have some thickness of this plate, which is delta X. And this surface has some area, A. So there are a bunch of parameters on which the rate of transferred energy will depend. So this specific case is thermal conductivity. We have thermal conductivity through the material. Why? Because the left side is heated more. If we consider this plate as a solid material, some solid state, internal energy is defined by vibration of atoms of this material in the crystalline lattice. So the high temperature, these atoms within this equilibrium position, which is defined by the structure of the crystalline lattice, they start to vibrate. The higher temperature, the high amplitude of this vibration. And obviously, if one part of this material is hotter than another, these vibrations will interact with neighboring atoms, and this excessive energy of this lattice vibration will spread across the crystalline lattice, and this process will result in some either equilibration of temperature, if we just have initial difference in temperature as a result of this thermal conductivity, temperature at both sides will become equal. But if we have some constant temperatures of different temperatures of two surfaces, this thermal conductivity will continue under steady state conditions. So this is the case. We have this T1 and T2, they don't change in time. And the difference between these two temperatures also doesn't change. So which parameters will define the rate of energy transferred by this thermal conduction mechanism? First of all, we need to consider parameters of the material. And for instance, if you take some wooden plate and copper plate, obviously heat will be conducted much better by copper than by wood. So the structure of the material, its properties, have to be taken into account. And there is a parameter, let's call it K, as a thermal conductivity, so called thermal conductivity, and defines the properties of material in terms of conducting heat. So it can be high. So for instance, for copper, the thermal conductivity will be high, and for wood, it will be low. Then second parameter, it will be defined by difference in these two temperatures, by delta T equal T1 minus T2. So obviously the larger difference in temperature, the higher rate of heat conduction will be observed. Another parameter which should be taken into account, this is distance between two surfaces at different temperatures, T1 and T2. So delta X. The smaller distance, less thermal resistance of the material, and more heat can be conducted. Another parameter is quite obvious, the area. So proportionally to the area, this will conduct more or less heat. So taking into account these factors, we can write that the power P, which is measured in watts, like joule per second, will be Q, heat, energy transferred, divided by time interval, delta T, and that is equal to K, thermal conductivity, times A, area, times dT over dx, like absolute value, let's take. So this, we have here actually all four parameters, but dt over dx is called temperature gradient, and it shows how like the rate of with which temperature changes with position. The higher this rate, so we have the higher temperature difference and the smaller distance over this change in temperature happens, the higher gradient, and thus the higher rate for thermal conduction through the system. So we can, for instance, if we have some two bodies with different temperatures connected with some rod with the length L, this gradient will be equal to T1 minus T2 divided by L, length of the rod. So in this case, it's quite obvious what will be the heat, like energy transfer rate when we have a uniform rod. But let us consider another case, which is a bit more interesting. This is again T1, T2, and we have two rods with made of different materials. So we have one rod and second rod. So there will be at their junction, there will be some temperature T, which is different from T1 and T2. And also there will be some rate of energy transfer, because T1 T1 is larger than T2 from left to right. However, here we need to keep in mind that these two rods connected in series. That's why, regardless the fact that they are made from different materials, in this condition, the power, the rate of heat of energy transfer of thermal conduction will be the same for both rods, because there is no other option. If certain energy per second is thermally conducted through rod 1, it will be also thermally conducted through rod 2. That's why the total rate of thermal conduction will be defined by the sum of properties and shapes of these rods. So taking this into account, we can write that P1, rate of thermal conduction to the first rod, will be K1, thermal conductivity of the material of the first rod, times area. A, it's the same for two rods, times difference in temperature between T1 minus T, which is temperature at the junction between two rods, divided by L1, which is the length of the first rod. This should be equal to P2, which is K2 A times T temperature at the junction minus T2 divided by L2. So from this equality, we can define T. So if we define T, this will look something like this. So T is equal to K1 times T1 times L2 plus K2 T2 L1 divided by K1 times L2 plus K2 times L1. So now if we substitute this temperature in one of these at the junction between two rods in one of the equations for P, for power, we can get expression for the rate of thermal conduction through this joint of two different rods will be A times T1 minus T2 divided by L1 divided by K1 plus L2 divided by K2. So this is the equation which you need to use for calculating the total rate of energy transfer during heat conduction when we have a connection of two materials, two bodies in series. So there is, by the way, this parameter L divided by K, like length or thickness of the material, and divided by thermal conductivity, its so-called R value, and shows the, like, in other words, this kind of thermal resistance of the material. That's important parameter when you deal with some thermal insulation in buildings or some structures. You want to know which material is better for thermal insulation, so you can have a thinner layer, but still which will conduct minimum amount of energy because of low thermal conductivity. So this is kind of some technical parameter which defines thermal insulating properties of materials. So another mechanism for energy transfer is convection, and that is happening when we have some joint, like simultaneous heat transfer with material transfer. So we have some hot, like warm parts of water underneath. When we start to heat up water in a pot, water underneath becomes hotter. Then because of increasing temperature, it thermally expands, so its density becomes smaller. And since it's in the gravitational field of Earth, it's replaced by heavier layers of water from the top, and together with moving hot masses like of water from underneath to the top, of course, energy together with this flow of water is transported upwards. So this is convection. And for instance, if we don't have, but you see that thermal conductivity and convection, they utilize presence of some material. If there is no material, we have the third mechanism of energy transfer is radiation. So any body in the universe which possesses some temperature not equal to absolute zero, like 0 Kelvin, radiates certain electromagnetic waves. So this is the mechanism how we get energy from the sun. The surface of the sun is heated up to about 6,000 degrees Celsius, and it's hot to that extent that it illuminates very bright light in visible spectrum, which we see, and also in UV and infrared, which we don't see. So it's quite broad spectrum of electromagnetic waves. And the total energy of electromagnetic illumination, which reaches the Earth, is so-called solar constant, which is 1,370 watts per square meter. So this is, let's say, intensity of solar irradiation, which takes into, like, includes all visible and infrared and UV parts of solar thermal radiation next to the Earth, but in vacuum, in space, because of reflection and absorption of certain wavelengths of this spectrum in the atmosphere. On the surface of the Earth at equator, when in the noon, when sun is in the zenith point, like states, it doesn't cast any shadows on the surface. We have about 1,000 watts per square meter intensity of the sunlight on the surface of the Earth. And you see, it's quite a lot. That's why solar photovoltaics is quite interesting and promising technology for future sustainable development, because we get so much of free energy, just 1 kilowatt per square meter. So that's quite a lot. Would be nice to utilize it in an efficient way. Okay, guys, I think that we are out of time. Thank you very much for attention. And Oops, sorry, this is not the right one. Yeah, be prepared for the midterm. Please read all problems, find the easiest, solve them, and then work on more difficult problems. And you will not lose any points. Okay, then wish you good luck and take care.
Excuse me, Professor.
Yeah.
Can I ask one quick question about the midterm?
Yes, sure.
Will we have like problems when we will have to integrate some formulas? For example, during the wave week on long upper, we had some problems like that, where we had to integrate the lengths and like dx parts.
Yeah. I cannot answer you this question. So if even you have something to integrate, that integral should be simple enough that you can do it within this dedicated time. So that should not be the, I believe, and I'm sure that the integral will not be the bottleneck point for solving the problem. If you understand the problem, no concepts of physics involved. If even integral will be in the problem, which I'm not sure, that will not be a complex integral, so will not be the biggest problem for you.
Okay, thank you very much. Have a nice day.
Yeah.
Goodbye.
You too, guys. Have a good evening. Bye-bye.